So class, welcome to chapter 2, and we are going to study in chapter 2 about what really derivative is. I'm going to approach it many different ways, so please keep following the video with me. So before we start, let's see that what did we study? We studied about rate of change. Then what is rate of change? Rate of change is a slope, and slope is what we usually say secant line. Also, we have another way of saying this is average velocity. That's going to be average velocity or average speed, like your mileage, like how long you can go per gallon, something like average mileage, something like that. So we are going to study that one, and then what happens if we take the limit from rate of change, slope or secant line average rate of change, that becomes derivative. If you take the limit here, so don't forget that's how it's gonna connect it. So let's try our appetizer one. Let's draw the graph. I want you to pause the videos and then graph it quickly with me. So I will do mine. So pause it and try yours too. I want you to do graphs as fast as you can. Oh, it should be 2,8, right? So let's just make it 2,8. We're gonna use that point, and then next one I'm going to use these points. Just basically what I did, I plug in 2, 1, 0. Okay, so that's what I did and mentally. So I hope you got this one. Then with this graph, we are going to answer next discussion question of 8. So first, what is the slope between 0 and 1? What is the slope between 0 and 1? So when you look at here, 0 and 1, I see that my slope is 1. First answer, that means 1. How about second one? Also 0 and 1, my slope is 1. I'm talking about these 2 points, so that's going to be 1. Then I want you to try next 2 as in-class activities. Look at next if you can find it. This one is also, as you see, 1. That one, I don't need to wait for you, right? You see, slope is 1. Then number 2. How about what is the slope between 1 and 2? So, second question now, what is the slope between 1 and 2? So this time, 1 and 2 is still 1. But this time, 1 and 2 is, I see as a slope 3. How about 1 and 2 here? It's gonna increase 7 when it goes by 1 because that was already 1. So 8 minus 1 over 2 minus 1, our slope formula. So I get 7 in this time. So what can I say? Definitely this one increases faster after 1 second. Next one, if I want to find the slope with these 2 points, oh, I said point 0 and 1, right? So it's 1 and 2. So in this case, 1 and 2 is going to be square root of 2 minus 1 over 1. So, oh, I get square root of 2 minus 1, which is square root of 2 is about 1.414. So I get 1.414 minus 1 is going to be 0.4. So I get slope as 0.4. This time my slope is 0.4. I should organize better. So what can I say? As you observe all those 4 graphs, they're all increasing. But how so? This one is a constant in constant speed. That means my speed is constant. Each time my slope is 1, my slope is 1. Or my average velocity is going to be 1 in this 2 segment. So that's going to be increasing. But however, how do they increase? When you see that after 1 to 2 seconds, there are differences. That means this one is increased faster after 1 second. This one is increased even faster than the other one. And this one increases still, but increases slower than before. So I want to see that differences all are increasing, but how? This one is going faster, faster, steady, getting faster, faster, like double fast forward, and then this is going to be going still forward, but about 0.4 speed. Yeah, that's what it means. Then, so if we found each section of this slope, this is from 0 to 1. This was 1 to 2. Then how about exactly at 1? What would that be? What would be the slope exactly at 1? That's what we're gonna study in chapter 2. So in this one was 1 and 1. Then this at this point has to be slope 1 for sure. This one is obvious. How about next one? If I slope 1, and then this one, this time was a slope 1, and next one was a slope 3, then add 1, what has to be this slope? What has to be this slope? And that's what we're gonna study. In this case, after you take the rate of change, and then that becomes 2. If you take the rate of change, and that becomes 2. Hopefully I have time that I can show you. And this one is going to, let's just do it. So x squared, if I'm gonna take the rate of change, it's gonna be a plus h squared minus a squared over h, right? And then I'm going to send h as a 0. I'm gonna do this one very fast. So I see that a squared plus 2ah plus h squared minus a squared cancel out. So I have a 2ah plus h squared over h, and h is going to be factored out. So I have a 2a plus h, and h cancel out. Look at, so I got my rate of change as a 2a plus h. If I'm sending limit as a 0, then this cancel out as a 0. So as previous section we talked about, I got the slope formula, derivative formula, which is 2a. But now I wanna find the slope at 1. If I plug in at 1 here, then it shows as my rate of change when sending to limit, which means the 1 point slope with 1 point, I get 2. That's what I'm talking about. I want to see the big picture here. So what is the slope at 1 exactly? Then I got 2. Did you have a wow moment? Hopefully you did. Okay, so also why do I know that that's 2? IVT, intermediate value theorem. Do you remember 1.8 or 1.7? Since it's a continuous function, my number has to be between 1 and 3 no matter what. So my slope is 1, my slope is 3, then no matter what, my slope has to be lying between 1 and 3. I cannot say that it's 2. It can be 2.1 depending on, but it makes sense. So next one, also this one, if you take a rate of change and plug in, then also that will give me exactly what the slope will be at that moment. So for me, with my experience, I think my slope is 3. My slope is a 3 at 1. And then this case, do you think my slope at 1 will be bigger than 1 or smaller than 1? It will be smaller than 1. It will lie down between 0.4 to 1 by intermediate value theorem at 1, because it's a continuous function and previous slope was 1, other one is 0.4, so this slope has to be between these 2 points. And then same thing, you can do rate of change in order to find that. Yeah. Do you want me to do it? I see the answer will be 1 over square root of 2 something. Anyway, you can also try if you want. So I actually put the circle here. The reason I put the circle, this one was a circle with radius 2. So I will just do it here quickly. If I do a circle with 2, then at 1, how are we gonna find the slope? How are we gonna find the slope? As you see, circle is not a function, right? And then in order to use rate of change, doesn't look like easy. So when we have a circle, which is not a function, we have a different way of taking rate of change, which we call as implicit derivative. Implicit derivative. So just wait for this section when it comes about 3.7 something. Yeah, I think so. Okay. So I hope that was a little bit good review. So with the previous example, hopefully you guys understand why we've been studying rate of change. Why we've been studying rate of change? Because when you're taking limit of rate of change, that's going to be our speed, or that's going to be derivative. And remember that rate of change uses 2 points. Like basically starting from San Francisco driving to LA using 2 points, and let's say it takes about 6 hours to drive, which means it's going to be distance divided by time. That's going to give me speed in here. So rate of change in this case, using time and distance, turn it into be speed. But if you're using 2 points, that's going to be average speed. Like you are driving down to LA, 80 miles per hour. I know you drive fast. Or if you wanna just use the instantaneous moment, oh, when you are on the highway 5, my speed is 80. If you're using 1 moment of the time, then that becomes more derivative definition using 1 point. So we measure speed by distance divided by time, and then we're gonna have 2 points. So I want you to see what's the difference is average speed versus instantaneous speed. Average speed, as I explained, is going to have A to B. We are going to have 2 coordinates, 2 positions, 2 locations, versus instantaneous speed is at that moment. At that moment. So this one's from LA to San Francisco. Then in the middle of the, where will be? Where you stopping in the middle? Then where one of the town, at that moment your speed will be 80 miles per hour or 75 miles per hour. And if we have also 2 points, another way of saying is a secant line is actually 2 points of average speed. And then you guys have heard about tangent function. Why we say tangent line? Because the tangent definition is y over x, right? That means rise over run with 1 point. If the secant line was with y2 over y1, x2 minus x1, then that's actually taking limit x goes to x2. Then it becomes y over x, which is our tangent definition. So we say that with 1 point that becomes a tangent line. So remember, tangent function is very important. It connects your linear equation to trig function through the tangent function and circles. So let's look at some of the definition. What is the average velocity? I promise you guys explain to you the definition of the rate of change. So when I have A to B, then my A value and output is going to be f of A. B value is going to be f of B. Then if I want to find rate of change, it's going to be f of b minus f of a over b minus a, which came from y2 minus y1 over x2 minus x1 as rise over 1. Youngah, you've been talking about now a to a plus h. Where does that come from? Look very carefully. I'm using same way. So if I have a, it's going to be input a, output is f of a. A plus h is going to be input, and that's f of a plus h. Then I'm going to put this one into the formula, f of a plus h, y2 minus y1 over x2 minus x1. If you see it, I still have 2 points, then they cancel out as you see rate of change formula. So basically they are the same thing. One of them starting from A and then terminate point. That's A to B. Then terminate point here is gonna be San Francisco, that's LA. Then what is the differences? This one is a San Francisco, and then from San Francisco you are going to add some more. How long? Up to the time how much you observed. So a little bit different of the concept. This one is the initial point to where you arrive. This was the initial point to how far, how much time you drove more. So San Francisco plus 5 more hours later. That's what it means. Little different meaning there. So average velocity, I want to make it instantaneous velocity. What does that mean? We've been mentioning it a lot. There's 2 coordinates to 1 coordinate the moment of this speed. So I need to send the limit here. Careful. This time I'm going to send the limit where to where? B goes to A or A goes to B, because you want to make the gap very close. Or if you're using this one, as you saw many times, if you are sending limit as H goes to 0, because I want to make this value very tiny enough. So look at why I want to make B goes to A, because I used to have these 2 coordinates in order to find my slope. But whenever you making that gap is H, I want to make that gap small as possible. So first this one was your H size. Now I want to make my H this much. If you're observing 5 hours, I want to observe only 1 second. Then I'm making my H value closer, 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 so that I can have a better accuracy of the slope at that moment. That's what I am doing here. That's what I am doing here. So A to B, you want to make that point. B goes to A. So B is going to A. Close enough. Or you can make H gets smaller. H value gets smaller. The gap gets smaller, so that you can almost look like an illusion of a 1 coordinate. That's what limit means, the number around it. So I hope that this explanation helps you, and this was actually very important explanation. We'll repeat one more time, probably behind on the paper. So keep listening. Thank you. So did you guys understand last section and last appetizer? Okay, a little bit deeper meaning of appetizers. So keep watching. And main dish is going to be analyzing a little bit more of a rate of change again. So we are going to review what tangent line means. What does a tangent line mean? That is actually rate of change with limit. Limit with rate of change. Then are we having 2 points or 1 point? Tangent line is going to be 1 point slope. At that moment, secant line is going to 2 different coordinates. Then let's read the question. Find the instantaneous velocity at 1 of function x squared. So we actually know the answer because we saw that earlier. I did it for you earlier. Oh, I shouldn't do it. Then we saw the answer at 1 was 2. And I show it to you algebraically. So probably you can practice algebraically one more time, but let me see if you understand from here to here. I have a function which if I graph it, it's a parabola. And now at 0, at 1, at 2, you see that the slopes at that moment are all different. So what is the slope at 1 here? That's why I'm asking. Why is the slope at this 1 here? Then when you look at this one without this information, I wonder, do you guys see as a rate of change? For me, I see rate of change as a plus h squared plus minus a squared over h. Do you guys see that? Already by plugging this one into rate of change, I need you to see this, not me. So from here to here, rate of change when you plug in, that is going to be this one. And algebraically, what they did, I just plug in f over a plus h, f over a over h. That's what I do it. So what I've been explaining is algebraic way. I see the a plus h. If you don't see it, just keep watching me. That's here. Then what is my x value? The reason for me I use a lot of my students get confused x plus h and then x. So I just choose a, but you can think as a is as input of x. So a is 1, which is going to same as x is 1. If you plug in here, do you guys see that 1 plus h squared minus 1 over h? Exactly, that's rate of change. So they are asking what is the rate of change at 1? That's what I want you to see. As soon as you see this one, looks like a rate of change. Yes, what function would that be? Which is function as x squared, where? At 1. So I want you to see this is rate of change x squared function at 1. Once you practice, you will see it, and then whenever it comes up, I will keep telling you. So I actually solved this one algebraically, almost there. Then, if it's algebraically, I have to take the limit. Where does h goes to? H goes to 0. So look at, can I plug in 0 in this case? No, I cannot. As you see, I cannot have something over 0. So we need to simplify this guy, which will be 1 plus 2h plus h squared minus 1 over h, and cancel out, factor out by h, 2h plus 2 plus h over h. Again, I can reduce it, and don't forget I need to send the limit h as 0, limit h as 0 over 2 plus h, then I get 2 as my rate of change. I get 2 as a rate of change, which we did it before. If you want to do it one more time, do so. I kind of approach it a little bit different way. Earlier one, I approached from function and plugged in. This one, I plugged in my x value and then find my equation, very end. So just look at slightly different approach, but they are the same thing. So how about before we know about rate of change? How those other people calculate it? Of course, they use this one, but another way they approach was just plug in very small number of h. So as you see that this is a formula of a rate of change at 1. I'm not talking about at 2, I'm talking about at 1. If it's 2, it's going to be 2 plus h squared plus 4 over h, right? So at 1, then what would be the slope around that point? So if they say h is 0.1, they basically talking about 1.1. Why is that? Because a plus h is 1 plus 0.1. So what is the slope at 1.1? That's what they're talking about. So if you want, please try to punch into calculator. And when I punch into calculator, I got actually 2.1. Yes, I got 2.1. And also, I punch into the calculator, this one too. Try to punch into calculator, it's not easy punching in. And I got 2.01. So this number represents 2.01. This represents 2.1. What am I talking about? We're talking about A plus H. H value is that. Then how about this number? What are they talking about? We're talking about 1.99. At that time, what is the slope? I get 1.99 by plug into calculator. I did plug it, so plug in. And this means 1.9 as my x value. Then what is the slope at that time? I get 1.9. So with your observation, then what is the slope at 2? Slope at x is 2. Then you are going to get slope is going to be also 2 as well, because by observing it is limit, this one is x approach from 2 plus, this is limit as x approaches 2 minus, both heading to 2, that I can conclude numerically the limit is 2. The rate of change is 2. The slope is 2 at 0.1. Oh, I put it this one wrong. So when when x is 1, slope is going to be 2. I think that's what I meant. Sorry if I confuse you. When x value is 1 and around 1, oh, it should be 1.1. I put it this one wrong, right? I was thinking this way. Sorry about that big mistake. And whenever my numbers around 1.1 or 0.9, that slope is going to be 2. Okay. So there's one more question right below, and I want you to think about same way. I want you to try numerically. Please punch into calculator and check. I want to try also algebraically. You can approach it this way or rate of change way, and then compare the answer for me. Good luck. Okay, class. So in class activity 2, hopefully it goes okay with you. And I did the rate of change first. So if you actually did rate of change, compare the answer. But if you didn't, do it and pause it and then compare my answer with me. The reason I didn't fill it up here because I thought that it would be nice to go over together with you. So just do the rate of change without mind looking at it, and then see that if you got the rate tangent function here. And now let's see that what do I like to estimate. I know that my function is 1 over x. Then I know this is 1 comma 1. I wanna figure it out. What is the slope at 2? That's what they're asking right here. Then what will be the limit I need to estimate? I'm estimating the slope, which is rate of change. This is rate of change. So I'm going to plug in, and that's what am I getting here by function of 1 over x. But where is it gonna be? Now I'm looking at my x value as a 2, which is my a value as a 2. So if I wanna look at as, rewrite as a limit notation, I can write it 1 over 2 plus h minus 1 over 2. This is the function I'm taking limit of. Where did I get that? I have my rate of change function. I rewrite it, and then what point am I looking at? I'm looking at my value of x as 2. So this is a limit. I like to find it. Then I don't know if you can guess what limit will be. I cannot really see it either. Kind of 1 over 2, 1 over 3, 1 over 4. So, oh, this one already showed that, because now I have a formula about what is the a value. as a 2. Why the x value was a 2? So as you see, it shows that slope at 2 has to be negative 1 over 4, which is negative 0.25. Does it kind of look like that for you? Okay, so we solve this one algebraically. Of course, you can do rate of change, the same thing, and sending the limit will give you exactly same answer. Then let's try to do numerically. Young, how do you do numerically? Well, we gotta punch into calculator. So what am I punching in? We are punching in this number. That's why I want you to be able to find it. So what are the h values? I'm going to plug in these values each. So give me a second to punch into calculator and I will write it down. Why don't you do same thing for me again? Because punching in calculator is not simple here. So pause it and try. So did you get to fill up the table? And after I plug into calculator my rate of change, and then by plugging h value small enough, I got those 4 values. And as you see that they are not symmetric compared to the other answer. And why would be? Why is that? Because I know that my function of the 1 over x looks this way. And at 2, as you could observe, before 2, my slope is going to be 1.9 like this. And 1.99, 1.9, oh, I did 2 extreme, right? But that as you see that my slope is going to be a little bit less steeper each moment, but never gonna be parallel, right? Parallel to x-axis. So here, and then here, and here, this way. So as you see, my slope is gonna be around there, a little bit less steeper. Whatever the x goes to bigger, so as you see, my number is gonna get smaller. Then what is the limit at 2? And as you see, 0.24, 0.3 is going to be from right hand side of the limit coming to negative 0.25, and then left hand side of the limit to from negative side also coming to 2.5. So I can say that my limit exists and then it's heading to negative 0.25. That's the answer. So I hope that you understand the meaning of numerical approaching and then algebraical approaching. I put a couple of questions on your homework, so I want you to practice one more time and keep understanding this one so that you understand next section, this chapter better. And good job. So if you look at the handout, there is a average rate of change and instantaneous rate of change, which means average velocity and instantaneous velocity, secant line, tangent line, right? So I want you to try to write the formula one more time and compare with me. So I hope that now you remember what each of the meaning is, and then keep practice with me. So we are going to continue dessert. Okay, dessert part of the 2.1, and we are going to keep studying about instantaneous velocity. Instantaneous velocity means a tangent line, and then that means a derivative at the graph. And then also remember the tangent line, the rate of change we found, that is itself a function. So those who are going to be computer science major, you are learning how to computer programming. And I will summarize one more time in the dessert part with our same example. The reason I'm using same example because I want you to get familiar, and then you're gonna do one more time with your example again. So let's do one more time here. Now I wanna see that graph my function. And I want to find the average velocity between those 2 points. If it's a velocity, my input is going to be time, and the output is going to be distance. So I want to see that between 2 to 3. So now we need to draw even 3. So when we have a 3, my coordinate will be 9. If I have a 2, then my coordinate is 4. So I want to find the slope between 2 and 3. So I see that 9 minus 4 over 3 minus 1 gives me, 2 gives me my slope as 5. Then this time I want to find the slope between 3 and 4. So I need to find my coordinate of a 4. That's gonna be 4, 16. Then same way, putting into rate of change, what do I get? It is going to be 7 over 1, that I get 7 as my slope. Then 2 to 3 is 5. So 2 to 3 is 5. And then here's a 7. Then what about exactly at 3? I see that some of you guys are guessing 6. Actually, this time 6 is a correct answer. But depending on graph, some graph can be 6.1, 6.2. This is coincidentally you got the correct answer. So that's going to be 6. Then what about at 3? So how are we going to compute? My guess is going to be 6. And then let's approach this one by taking limit of the equation numerically and then algebraically. So what are we looking for? I want to estimate the rate of change. So I'm going to approach algebraically first, because when I plug in this one, my function is going to be f of a plus h plus f of a over h, and limit h goes to 0. So I get x a plus h squared plus a squared over h gives me, I'm gonna omit some work because I did that previously twice. So you see it becomes 2a plus h. That h goes to 0. I ended up with 2a as my formula. Then from here, I see what is my a value. A value is the same as my x value. X value at 3, what I want to find. My slope will be, now have a function form. So this is gonna give me 6. Okay, I'm gonna go quickly what this means. So I found the function of the slope, which means I made a coding equation here. So if I have x as 3, then my slope is gonna be 6. If my x is 4, then my slope is gonna be 8. If my slope is 50, then at 50 of my function, if this was 50, then what is going to be slope over there? It's going to be, by plug-in, you see the slope becomes 100. So basically, I want you to see that we made a formula for rate of change of that given function. So this function has a formula. What is it? The formula is 2a. You can say it's a 2x. Then what is this? Whatever you plug in x value now, that will give me my slope or rate of change. And that will be related to differential equations in the future. Okay, so now I got this one. And what should I write? What am I estimating? That's confusing, right? So that coming from right here, I have my rate of change of a function using t squared. Where at? I'm looking at x value is 3. So I can rewrite all the x over a value as 3. So it's going to be 3 plus h squared minus 9 over h. So I want to find the limit of this function. And as you see, if I plug in, I cannot find it. But after you do algebra, as you see, denominator cancel out. So it turned out to be 2a. And the limit is actually going to 6 at x is 3. Then how can you check numerically? I just need to punch in my slope. So this is the slope, right, class? At 3. So now I'm going to plug in h value carefully into the calculator. So I will pause it and then write down the answers. You can try same way as well. So after I plug in the value of 0.1, 0.01, each of the XS, HS, my rate of change, I got given values. So as you see that my right hand limit x from the 6 plus, it goes to 6, and then as x comes from negative side, also 6. So there's a limit of the rate of change will be 6, then the slope at 3 is going to be 6, which you see it as a numerically with the graph. We checked it approaching left side and right side, and then by algebraically we approach it, and then that also gives me 6. Okay, so I hope that that was a kind of clear example of what is going on, and there will be one more question below you. And let's finish this one, and then good job everybody of this section 2.1. So let's compare in class activities 3, our dessert, compare the answers. So my graph looks this way, and then see that A from 2 to 3, my slope is negative 1 over 6. B, I got using slope formula, I got negative 1 over 12. So my guess at 3 will be lying between negative 1.6 and negative 1.12. So I will just guess the negative 1 over 8, something like that. That's just my guess. Okay. So how are we gonna find that algebraically? If you look at my work, we actually did it previously in class. I'm sorry, I made a mistake earlier. One again, I think I put it as accidentally 2a. A times A is A squared, right? I'm really sorry about that confusion, and I want you to fix this one. So it's going to be negative 1 over A squared, and that was a very big mistake. So change this is the correct way. So that's what I got as my rate of change function. You can see the work. Then where is my x value? I want to find when x is at 3. So my function shows negative 1 over a squared. Then that is the formula of the slope. Now derivatives, formula is derivative. Then at 3, I can plug in as a, I get negative 1 over 9. So my guess is close enough, and actual answer is negative 1 over 9 at 3. The slope is going to be. Then let's check this one numerically. In order to check numerically, we need to find the limit notation. So how are we gonna rewrite this one as a limit notation? Look at rate of change function here. I had it. What am I looking at? I'm looking at rate of change of the x value at 3. So all the a I can rewrite as 3. 1 over 3 plus h minus 1 over 3. This is a slope formula that I like to see where slope is going around 3 of 1 over x function. So if you want to see it, I want you to punch in those values and then figure out those numbers. Let's pause the video quickly. Okay, by plugging my values of h in the rate of change, I got those 4 values. Then I'm looking at the slope at 3, and can you guess what you are getting? So I see that the number is going to be about negative 0.111. Okay, so let's punch in what is 1 over 9 is. If I punch in 1 over 9, oh, that actually gives me 0.111111. So as I guess, my limit is going to be 0.111, which is negative 1/9. But as you see my graph, by the time, when time is going by, is the slope is increasing or decreasing? So my slope is actually decreasing, but it's each time also is getting smaller and smaller. So you have to see careful. I have my slope this way, and then each time go by, it's gonna be a little bit less stiff. So whenever it goes here, it's gonna be a lot more look like a parallel to or meeting the x-axis. Okay, so I see it. I want you to make sure understand how we approach it numerically, finding derivative or find the rate of change or instantaneous velocity. Also find how we approach algebraically, and then you will see this kind of example quite often. So I show that we can find it 3 different ways, 1, 2, and 3 in here. Okay, so that's it for 2.1, and good job everybody.